Hello, let's discuss Appliance Inventions, one of the problems from the 2026 British Informatics Olympiad. Here is a statement. I'm not going to go through it as usual. I'm going to explain the problem on a whiteboard. Feel free to read it in the description if you wish. So, what's the problem? The problem involves these n by n grids, so these square grids, and each grid is made up of A's and B's. In the problem, these are aluminium and brass widgets. And the aim of the problem is to transform this grid into another grid, into such a grid that there's an adversary in this problem. There's an AI adversary that shuffles the rows of the grid. And you want to get to such a grid so that however your adversary shuffles the rows, you can shuffle the columns to return the grid to its initial state. So that sounds a little complicated, so let's go through an example. So let's call the type of grid we're trying to reach let's just call it stable. Why not? So we want to know how many moves we need to get to a stable grid. And so what's a stable grid? Is this a stable grid, for example? This is actually not a stable grid. So because our adversary can shuffle the rows in such a way that we cannot return the grid to its initial state by shuffling columns. By shuffle, I mean permute, more formally. So our adversary can permute the rows, let's say by permuting them like this, like that, like what I just drew, or just swapping these two and leaving this one where it is, doesn't matter. In that case, we would end up with this grid. And then however now we try and permute the columns of this grid, we cannot restore the grid to its initial state. So this grid is not stable. Let's call that stable. This is terminology that isn't in the statement, but this category of grids doesn't really have a name, so we're just going to call it this. And so we want to find so this is not this grid is not stable. But if we change some of these letters, if we change this A to a B, and these three B's to A's, we'll get this grid. And this grid you can actually check is stable. However you shuffle the rows. For example, if you shuffle the rows like this, then in the same way, you will get if you shuffle the rows like that, you'll get this grid. And then we can shuffle the columns of this grid back. We can shuffle the columns like this. This column can go here, and then these columns can shift back this way, and then we'd get back to the original grid. You can see that. And so this grid is actually stable. You can check that for any possible shuffling, for any permutation of the rows, you can get back to the original grid. So this grid is stable. And so we said that how do we get from this grid to this grid? We just flipped this B to an A, this B to an A. So the number of these positions that you change is the cost, basically. And we want to find, given an initial grid, what is the minimum cost, what is the minimum number of these A's or B's we need to change to their counterparts, to the opposite one, value, to get to a stable grid. So that's the question. And in this case, we got to here with 4, because we changed these 4. But actually, we can change just 2. We can change just these 2 B's to A's, and then this is also a stable grid. And then you can see this is stable trivially because our adversary shuffling the rows will actually not affect the grid. So we don't even have to shuffle the columns at all, because shuffling the rows just leaves the grid the same, because every row is just the same. So that's the problem. And as for constraints, the size of the grid is up to 256 by 256. So it's not a tiny grid. So how do we solve this problem? So, you might start thinking about this problem, and one of the first observations you might make is something like, you might start to think, why did this original grid not work? And one of the trivial things you can say about it is that if you count the numbers of B's versus A's in each row, obviously if you just count the number of B's, let's say, then that tells you the number of A's. That's just n minus that. If you count the number of B's in each row, if they're the same in different rows, then if they're different in different rows, then it's definitely not a stable grid. Why? Because if our adversary swaps two rows with different numbers of B's in them, let's say in this case we have one row with 1B, one row with 1B, one row with 3 B's. If our adversary swaps these two rows, then we'll end up with a grid with a different list here, with like 1B in the top row, like we have here. We'll have 3 B's in the bottom row, 1B and 1B in the top row. And now our shuffling columns doesn't actually change any of these numbers, because we only permute the values within each row because we're permuting the columns, but we don't move values between rows. And so these values will stay the same, and so we can't get back to the original grid. So you might say something like that. So a stable grid has to have the numbers of B's in each row has to be the same in a stable grid, for example. That's one thing you might spot. The same doesn't apply to columns, by the way. This isn't a symmetric problem. But so that's something you might spot. That's true, but that's not a useful direction actually for this problem. That's not a particularly useful direction to go in. So, well, what is a useful direction to go in? Let me just copy this and move down a little. And let me present the first observation in the solution. So if we look at this grid, let's remind ourselves that our adversary permutes rows, and we permute columns. So once our adversary is done with their work, they'll leave us with a different grid, and we have to shuffle the columns back so that we reach the same original grid that we started with. And this means however our adversary messes with the rows, the set of columns that we have left has to be the same as the set we started with, because we have to then be able to permute those columns to get back to the original grid. And this means, more specifically, any column that is in the grid once the adversary's done anything. So in this case, let's say the adversary moved us from this grid to this grid. Any column that they leave in the grid had to have been in the original grid, right? And in this case, that's not true, and that's an issue. So this column, for example, the adversary permuted these rows, and this column that they left us with is not in the original grid, which means however we shuffle the columns, we can't get back to the original grid. And, well, what is this column? This column was just a permutation of this column that arose because of the way that our adversary permuted the rows. So our adversary can get any possible permutation of any column we started with might be a column that they leave us with. in this middle stage of the game. Because they can just put, if they want a certain permutation of this column, they can just permute the whole set of rows that way, and that permutation just applies to every column. And so this means that they can leave us with any permutation of any column that they want, of any specific column. If they choose a specific column, they can leave us with any permutation of this column. And we have to be able to get, and that column has to be in the original grid, right? So what we've observed is basically, for a grid to be stable, every permutation of every column, this is not great handwriting, has to be a column in the grid. And that's fairly easy to check because of the logic we just went through. If a certain permutation of some column isn't a column in the grid, then our adversary can permute the rows exactly such that that column becomes that permutation that isn't in the grid, and then we're just lost, right? So this is a necessary condition. It's not a sufficient condition. But so this is the first key observation. Any column that we have, every one of its permutations must also be in the original grid. But if you think about that, the next observation seems to come fairly naturally, that like most of these columns will have quite a lot of permutations, and they probably won't fit in the grid. That hopefully feels like a natural observation. That if you have, let's say, a 10 by 10 grid, because we said it was a square grid. If we have a 10 by 10 grid, and there's one column with 5 A's and 5 B's, for example, well, that has 10 choose 5 permutations, and that definitely won't fit in 10 columns, right? And so that means this kind of you can't have a column with 5 A's and 5, you just can't have such a column in a stable grid, in a stable 10 by 10 grid. And so we can try and say that something like this more generally, and you actually see that. So if we have a column with at least 2 A's and at least 2 B's, and let's denote those numbers with A and B, the numbers of A's and B's, they sum to n, obviously, then the number of permutations that it has, which have to all fit in the grid, are n choose A. And we can show that because of the nature of these binomial coefficients, because they like n choose 0, which is 1, is, and n choose n are smallest, and then n choose 1 is larger, and they sort of increase towards the middle, which is n choose n over 2, or n over 2 plus 1 if it's odd, n plus 1 over 2. But they increase towards the middle, and so n choose A, since this is fairly intuitive, that if both A and B, both A and n minus A essentially, are at least 2, then n choose A will be at least n choose 2. By the way, this also implies that since A and B are both at least 2, then n is at least 4. So this is at least n choose 2, and we can show that in this case, n choose 2 will be bigger than n when n is bigger than 4. So at least 4. So we've basically got that this kind of column just cannot exist in our grid, because it would imply that all of its permutations must exist in the grid, and there are too many of those. There are more than n of those. So this means that we cannot have any columns with both at least 2 A's and at least 2 B's. Which in turn means that we can have 4 types of columns in our grid. Well, essentially 2 types of columns, actually. So we can have columns that are all A's except for 1 B, And then the opposite, all Bs, or all Bs and 1A. Well, okay, I'll still write them out. All Bs, 1A. So we can have these 4 types of columns in our grid. We can have no other more complicated columns with bigger mixtures of A's and B's. But so let's look at these and see what they would imply. Are there too many of these? So let's look at all A's, 1B, for example. So if we have a column with all A's and 1B somewhere, we still know that all of the permutations of this column must be in the grid. And so that means, well, there are exactly n permutations of a column with n minus 1 A's and n 1B. So that would actually fill up the whole grid. So we need all the permutations of this, and we can choose whatever order we want to put them in. Like this. We can choose where all the B's go. I've chosen a very big grid for some reason. I don't know why. We can choose, but you can imagine filling in the rest of this grid. You can choose where the B's go, but you know what set of columns you have. You can just order them wherever you want. So we've deduced that if we have at least one column like this, with all A's and 1B, then that means all our columns have to be columns with all A's and 1B, and they have to be permutations. All the possible permutations of that fill the grid. So this is what the grid will look like if I had just filled in the rest of this grid. And so that's one option. Obviously, this would imply that the same thing happens if we have this case, just the opposite with all B's and 1A. So if we have at least one of these, of either of these types of column, then that fills in the whole grid, and we've got this kind of, all permutations of all A's and 1B or vice versa, and this ends up looking, it's a grid where every row and every column has exactly 1B. So this is some kind of like rooks on a chessboard style grid, where like a placement of rooks in every row / column so that they don't attack each other. And so this is one type of valid of stable grid, and you can check that it is stable. So this is one option, and the other option is that you have none of these. So every column is one of these two, either all A's or all B's. And in that case, I'm going to draw a smaller grid here, but that case will look something like this, right? So we have just uniform rows. So these are the two cases we've narrowed it down to. And if you actually check the look at both of these cases, they are both obviously stable. So we've found what it means to be a stable grid. You're either a uniform grid where each column just is like one column of exactly the same value, so it's uniform within each column. And this is obviously stable because permuting the rows doesn't do anything. And the alternative is you're this Rook type of grid. And in the Rook grid, it is also stable, because however you shuffle the rows, you can shuffle the columns to bring whichever B you want back in the same place. Because when you shuffle the rows, you will just end up with the same set of columns. This is very easy to see. So we've turned the problem into, we've now understood what a stable grid is, and now we need to find the closest distance from a grid to a stable grid. And so now the problem becomes, given a grid, what is the minimum number of entries you need to change in the grid to get it to one of these two types of grid? And so we can solve the problem separately for all the types of grid, and then just take the closest distance and output that. So we need to solve it separately for these types of grid. And so the uniform case is relatively easy. So what's the closest distance from a grid to a uniform grid with uniform columns? You can solve this individually for each column. And for each column, you just go through the column and just the distance from that column to a uniform column is just the number of A's or B's, whichever one's fewer out of those two. So the distance to a uniform grid is pretty simple. Now, how about the distance to a Rook grid? The distance to a Rook grid, again, there are two types of Rook grid we want. The ones with all A's in them, and one B in each row / column, and then the opposite, the ones with mostly B's and one A in each. We can again solve these two separately. But so let's say we're trying to find the closest grid that looks like this, with mostly A's and then one B. The B's are the Rooks, basically. I've replaced in this diagram, I've replaced the A's and B's with the zeros and ones, actually, just because they're slightly easy to tell apart. So instead of us wanting to have exactly one B in each row and column, now let's say we want to have exactly one in each row and column. And so we want the closest distance to such a grid, right? And if you want to figure out the closest distance to such a grid, it turns out to be, well, this is fairly intuitive. You want to keep as many of the ones that you've already got as possible. So if you want exactly one in each row and column, in this case, there's actually a way of keeping all the ones you've got. Sorry, not all the ones, but keeping 5 ones. And then you only have to change this 1 to a 0. So in this case, you only need to do one change, actually, to get this to such a grid. But so if you look at this problem, it's actually analogous to finding how many of the ones that I've already got can I keep? What is the largest number I can keep? So if the grid was slightly different, if this was a 0, the answer here would be 4. And so I can figure out that these 4 ones are already in their correct places, and they don't attack each other if they were Rooks. And so if there are 4 ones that I can keep, then I've got to change, I've got to flip all the other ones to zeros. So if there are, let's say, C1 ones and C0 zeros in the whole grid, then I've got to change C1 minus K. If K is the number of ones I can keep, then I've got to change C1 minus K of the ones to the rest of the ones that I'm not keeping to zeros. And in this case, I've only got 4 ones, so I need a 5th one. I need to fill that number to n to get the rest of the ones. So n minus k of the zeros that need to be changed to ones. So is this sum here is our cost. And if you expand this out, you get n plus c1 minus 2k. And n and c1 here are constants for a given grid, for a given starting grid. And so we basically just want to find the largest number, to minimize our cost, the largest number of ones that we can keep in the grid. And in this case, we could have spotted that we could have also spotted, let's say, we could have said, let's keep this one and this one, but then that would have stopped us from keeping these two ones because they're in the same row or column as this one. So if we'd said this one, and this one, that would have been 3 ones that we keep, but that would have been a higher cost to get to that position because it involves removing these 2 ones instead of just removing this 1, and also adding an extra 1 in this column. So each one we miss adds 2 to our cost. But so we want to find in this grid the largest subset of these ones we can keep, basically. So that's the new problem, and then we can just use this formula to calculate the cost. That's a new problem. Given a grid of zeros and ones, given a binary grid, what is the largest number of ones that you can choose such that no 2 are in the same row or column? Right? And this can actually be nicely formulated as a graph problem. So in this case, if we number the rows from 1 to n, and we number the columns from 1 to n, we can now make a graph between the rows and columns. And the ones that we want 1 of each of in each row and column will now become edges, right? So these will become edges. And so in the grid, we see that there's a 1 in row 1, column 1. So that means we'll draw an edge between the two. There's 1 in row 2, column 2. So we'll draw an edge between the two. There's 1 in row 3, column 2. So we'll draw an edge. There is 1 in row 3, column 3. So we'll draw that edge too. And there's 1 in row 4, column 5. So we'll draw that as well. And so now the original problem was find the largest number of ones we can choose in this grid so that no 2 are in the same row or column. Well, if you translate that now into this graph, into the language of this graph, the ones have become the edges, and the rows and columns are the nodes. And this is bipartite, the graph. We've only got edges between the halves. So if you actually look at the problem, it becomes find the largest number of edges you can choose in this graph so that no 2 of them share a common node. And so that means this edge and this edge together are fine, for example, because now they don't share a common node, and that corresponds to these 2 nodes being fine chosen together. But this edge and this edge are not fine together, and that corresponds to these 2 ones being chosen together. So that's an equivalent problem. But now that is, hopefully to some of you, a known problem, which is the maximum matching problem. This is the maximum matching problem, and finding the size of a maximum matching is in a bipartite graph, in a graph with two halves like this. Can be done in n squared m time, where n is the size of one of the halves and m is the size of the other half. I mean, in this case, n and m are equal, so this is just n cubed. So yeah, we can find the maximum matching in this graph. So in this case, we can say choose this edge, choose this edge, choose this edge, choose this edge. Now that's 4 edges. And that corresponds to choosing the ones that we've circled I don't even need to circle them. Again, the ones that we've already circled in the grid. And so, yeah, that's solved the problem. That's it. So if we recap, we showed that the original problem of finding the distance to the closest stable grid, we've shown that a stable grid is either a grid consisting of rooks that don't attack each other, or a grid consisting of n rooks that don't attack each other, or a grid of uniform columns. And we can find the shortest distance to each of those separately. The uniform columns is trivial, and the rook case boils down to a maximum matching, and we run that twice for both ways round of A's and B's being zeros and ones in this graph that we've got. And we run all of those, and then we take the minimum. So that's the solution to Appliance Inventions. That is it. It's quite a neat idea. I think this was the nicest problem in the set. Yeah, that's about all I have to say. See you in the next one. Check down in the description for links to the other solution videos.